recall that if the limit of a function as its independent variable x approaches a is infinity, then we say that the limit of that function does not exist as x approaches a, as is the case right here. X is approaching, let's say, 0. As x approaches 0, as x gets closer and closer to 0 from the left and even from the right, we see that we are taking, f of x is taken to infinity. And we know that, but what I want you to take note of now is the fact that this is not a continuous function. Because to draw this curve, we had to, as we discussed in the very first video, draw this curve, draw this part, and then take the pen up and then come down here and draw this other part. So this is not a continuous function. And then let's look at another example or another reminder of a function that is whose limit does not exist as x approaches a number. We looked at functions whose right hand limit is not equal to their left hand limit. So for example, we have a piecewise function and the limit here as x approaches a, where a is right here from the left, we're seeing that this is the limit. Let's call this point b. Let's call this value on the y-axis b. But as we approach a from the right, we see that f of x is approaching c, and as such the limit does not exist because the right hand limit is not equal to the left hand limit. And again, take note of this fact that this and this, the two parts of this curve, have to be drawn separately, requiring that I lift the pen from the paper and then drawing the other part. As such, this function is not continuous. So what we're seeing here is that the non-existence of the limit of a function as x approaches a number a renders a function discontinuous at that point. A function is also rendered discontinuous if there is a hole in the graph, as is the case right here. So what exactly is happening here for this function to not be continuous? Well, we can come here and say that if this is a, then this is f of a. This hole in the graph here for this x value here, b, because there's a hole here, then there's nothing to correspond to an f of x value. So there is no f of x value or y value for this independent variable. In other words, we say that f of b is not defined. So we've just come to appreciate some important facts. That in order for a function to be considered continuous, then f of a must be defined. You must have a corresponding f of x value for the independent variables. What else? We also come to note that the limit of that function as x approaches a must exist. If it does not exist, as we showed with the case of the limit of, if it does not exist, as we showed in the case of the right hand side not being equal to the left hand side, or the infinite discontinuity, then the function is not continuous. So the limit of f of x as x approaches a must exist. And what we're going to do is that we're just going to put all of this in one equation that we will call number 3. And this is the condition that we're going to summarize it in and say, this is the condition that is required to be met for a function at a point to be defined as continuous. And what is that condition? Let's even write it in a different color. That condition is that the limit of f of x as x approaches a must be equal to f of a. So no longer do you have to ask yourself, when I'm drawing this curve, do I have to take the pencil off the paper or any question of that nature? You don't even have to look at the curve for a function to determine if the function is continuous. All we need to do is, having come to appreciate the concept of limits, all we need to do is just ask, is the limit of f of x as x approaches a equal to f of a? And if it is, then the function is continuous at that point. So let's look at a few examples. So if someone were to ask you if f of x equals 2x plus 1 is continuous at the point x equals 2, how do we figure that out? All we need to do is to determine the limit of 2x plus 1 as x approaches 2. If that is equal to f of 2, then without a doubt the function is continuous, and it is equal to f of 2 by direct substitution, leading us to the simple answer 5. And this proves that the function 2x plus 1 is continuous at x equal 2. So here we have this piecewise function defined for x less than 3 and x greater than or equal to 3. Now what we want to do is to find the value of a that would make this function continuous everywhere. In other words, we want this function to be continuous everywhere, and to do this we have to make the left-hand limit equal to the right-hand limit at x equals 3. So we're going to substitute x equals 3 into this function. And why 3 in particular? Because there's a crossover at 3. So this function is continuous for every x that is less than 3 and every x that is greater than 3. But we want it to be that there is no jump discontinuity at that point. And we do that by ensuring that the left-hand limit is equal to the right-hand limit. So that's why we're going to be using x equals 3. So we'll have that the log of 2a plus 12 is equal to the log of 3 plus 4a. And as you learned from module 1, that would imply that 2a plus 12 is equal to 3 plus 4a. And so a is equal to 9 over 2. In other words, a equals 9 over 2 is the value of a that would render this function continuous everywhere.